Last little piece here is Newton 3. For every body 1 which exerts a force on body 2, body 2 exerts a force on body 1 given by this equation, this vector equation. Now, this is the equal and opposite reaction law. For every action, there's an equal and opposite reaction. And this basically says I've got two bodies, and let's say they're moving towards each other. They hit each other and they exert forces. So this is body number 1. This is body number 2. And so body number 2 feels a force pushing it from body number 1. So 1 exerts a force on 2. But if 1 exerts a force on 2, 2 exerts the exact same force, but just in the opposite direction. So 2 exerts a force on 1 pointed in the opposite direction. So that's Newton 3. And we are going to use Newton 3. Newton 3 is actually really important, and we'll see how Newton 3 leads to the idea of momentum. Okay, before we move on from Newton 3, we can prove a really important and interesting result using this law. So let's do that. And so what we're going to do is imagine now a system of particles. So we've got a bunch of particles like this. And what we're going to try to do is figure out what this could be particle 1, 2, 3, 4, and 5, and 6. And what we're going to try to do is figure out what Newton 1 tells us about the internal forces in a system. So we really have two kinds of forces acting on this collection of particles. We have external forces, so for instance, gravity. Each of these particles could be accelerated by gravity towards the center of the Earth. Or if they were charged, there could be an electric field, and they would, of course, feel a force acting on them in the presence of an electric field, the Coulomb force. So there's external forces acting on these things, and then there's also internal forces. That is, these things are potentially bouncing into each other and exerting forces on each other and causing changes in accelerations as they move around each other. So let's imagine the ith particle. I'm going to use small letter f, and that small letter f is to indicate the force on an individual particle. I'll use capital letters to indicate forces and things like that on the entire collection. So total forces, total masses, and that kind of stuff will have capital letters. Individual particles, individual accelerations will have lowercase letters. So let's take the force acting on the ith particle. So what is the force acting on the ith particle? The force acting on the ith particle is the external force acting on the ith particle. I'm going to label that as ext on the ith particle. And this, again, could be gravity. It could be whatever is outside of our system exerting forces on these particles. Plus, then we're going to sum over, well, let's see. We want to think about, say, the forces exerted by particle 2 onto particle 1 and particle 2 onto particle 4 and so forth. And let's look at those. So we're going to sum over the j particles. So j is an index to count the other particles besides the one we're talking about. So I could be 1. Summing over j would be looking at 2, 3, 4, 5, and 6. I could be 4, and summing over j would be looking at 1, 2, 3, 5, and 6. Okay, so this is going to be looking at anything j not equal to I. So we're looking at all the other ones not equal to I, and we will see the force of that particular particle on the ith particle. And if we add all of those up, that will tell us the total force acting on our particle by the other particles. So this is what we would call internal forces. So these are again, these particles bouncing off of each other and that kind of thing. So now what we're going to do is we have all of the possible forces acting on our collection of particles, all the external forces and all the internal forces. So let's add all those up, and we'll call that the total force. So the total force, again, I'm going to use a capital letter to talk about forces exerted on the whole collection or system of particles. That's going to be the sum over I of all of the individual forces on each individual particle. Okay, and so what is that going to be? Well, it's going to be the sum of this thing. So we're going to add up. We're going to calculate this for each particle and then add them all together. So that would be a sum over I of the external forces acting on each of those particles. So that would be the external forces acting on each of the particles here. And then we would have a double sum now. So our double sum is sum over I, sum over j not equal to I of f j I. All right, this term takes a little bit of work to try to figure it out. So let's imagine that we just have 3 particles. So I'm going to get rid of 4, 5, and 6 because that will make life easier for us. And let's just sort of manually calculate this. All right, so what this says is sum over I. So we're going to start from 1, then we'll go to 2, then we'll go to 3. So starting with 1, sum over j not equal to I. So then I is 1. So then we're going to sum over 2 and 3. F of j on I. So the first term would be f of 2 on 1 plus f of 3 on 1. So hopefully you see this. We put our first particle is 1, and then we can't use 1 for the next sum, so we put 1 here, and then we just do 2 and 3. And then we repeat the process. So the next I will be 2. And so we'll have f of 1 on 2, and we will have f of 3 on 2. And then finally, we will have f of 1 on 3 and plus f of 2 on 3. So hopefully you see that this double sum here, this is just for this example. If we had 4, then we would have to keep going and add in the 4th one. But this gets all of the possible interactions. 1 on 2, 2 on, 1 on 2, 1 on 3, 2 on 1, 3 on 1, so forth and so on. So, but what Newton's third law tells us is that if we have an ij, then that's going to just be minus fji. This is equal and opposite. So in other words, here, this one, f1, 2, that is the exact same thing as minus f2, 1. And let's see, this f1, 3 is exactly the same thing as minus f3, 1. And this f2, 3 is exactly the same thing as minus f3, 2. So we can make these substitutions and see what we're left with. So I have an f2,1 minus an f2,1, those cancel each other out. I have an f3,1 minus an f3,1, those cancel each other out. And I have an f3,2 minus an f3,2, and those cancel each other out. And lo and behold, this whole thing just equals 0. So what Newton's third law tells us is that these internal forces all cancel each other out. So this whole term here just goes to 0. For every possible force that one thing is putting on another, it's counteracted by the force of this one on that one. And so when you add them all together, they just give you 0. And so what that tells us then, as I clear a little bit of space here since we don't need this anymore since it's all 0, what that tells us is that the total force here, the total force is this sum, and this sum is just the sum of the external forces. And this is an amazing result. It says that if you know the force acting on your collection of particles, your external forces acting on your collection of particles, then you don't have to know anything about the internal forces because they all cancel each other out, so you don't have to worry about them. And so let's see if we can work on this a little bit. So we'll see how this leads naturally to the idea of center of mass. So let's work on this a little bit. So what we can do here is we can think about that this is the sum over all the particles of the mass of each particle times the acceleration of each particle. Okay, so this is just, we're just writing F equals ma for each individual particle. So for each individual particle, we know that the total force is the external force acting on it. All the other forces cancel out, so we have mi ai acting on this piece, right? Because this right here is just we could rewrite this as f sub I is equal to mi ai. Okay, so we've done that. Now, what we're going to do is let's work on this a little bit and see what we get. So first of all, let's remember that there are a couple different ways of writing the acceleration. The first way that we can write the acceleration is as v dot. So we could write a as that's the same thing as the velocity, the time, the rate of change of velocity with respect to time, or that can also be written as x double dot. And this is just the second derivative of position with respect to time. So you see how is your position changing per second, and then you see how is your change of position per second changing per second, and that's what the acceleration is. So we can rewrite this as with this sum mi x double dot. All right, there's a fancier way for writing this in math, and I'm going to have to show you how to do that just because it will make the next part a little bit clearer. So if you have a second derivative, that's exactly the same thing as writing d squared x over dt squared. So this is just, again, this is just notation. This is notation, and it's useful sometimes to know the notation a little bit because it becomes helpful for writing these kinds of expressions. So the last thing that I'll write here is, as sort of changing notation on ourselves, is mi times the second derivative of position with respect to time. I don't think I wrote there. We need the arrow there. That's a vector. All right, so one of the rules about derivatives, and this is something you'll have to take a calculus class to understand, is that there are sometimes things that you can pull in and out of the derivative like it was a parentheses. You know how you can factor things in and out. Well, in a similar fashion, we can factor out constants, and we can also put them back in. So the mass of each particle is a constant, so I can take and stick that inside of the derivative, and that's not going to change a thing. That's the saying that the mass of the particle times the second derivative of the particle's position. This should be an I here to indicate that we're talking about the position of the ith particle. The mass times the second derivative of that position is the same thing as the second derivative of the mass times that position. In other words, we can do these in any order that we want to. And there's also something called a sum rule for derivatives, and you can do the same thing for sums. So we can also plug that in. So what we get is we get that this is equal to, this is equal to the second derivative with respect to time of the sum of over all I particles of the mass of the ith particle times the position of the ith particle. Okay. Now, what I'm going to do next is going to be confusing until we think about it. What I'm going to do is multiply everything by divide everything by the total mass. So all this is equal to the total force acting on the system. So what I'm going to do is divide everything by the total mass. And again, I'm using capital M to indicate total mass. What is that going to be equal to? That's going to be equal to the second derivative with respect to time of the sum over all the particles, adding up all the particles, mass times their position. And we're dividing through by m, but m is a constant. So just like here, I took this m and pulled it inside, I can take this m and pull it inside. And so what I get is this quantity here. Now this thing is an interesting thing. Look at what it is. It is it's really this whole sum is an interesting thing. This whole sum is an interesting thing. What is it? This is the average. This is the average position. So you take all of your particles in your system, all the particles, however many particles you have, and you set up a coordinate system and you imagine trying to find the average position. What's the average position? Where's the most likely sort of place to find a particle? But it's not quite the average position. It's the average position weighted by mass. Meaning, notice mi over m, that's just the fraction of the total mass that particle has. So let's say what we would do if we were calculating this for particle 2, we'd take the mass of particle 2 and divide it by the total mass. And that's essentially the percentage, not, it's a fraction, not a percent, but it's essentially the percentage of the mass of this whole system that's in particle 2, how much of the mass is located in particle 2. And then we're multiplying that by the position of particle 2. This is the position vector for particle 2. And then we add that to all the rest of them. And so this is actually called the center of mass. And it's sort of like you look at all of your particles, and the ones that are the most massive contribute the most to this position, and the ones that are least massive don't really matter. So what we're going to do is call this center of mass, since it's sort of the central position of the entire mess of particles here, we're going to call that center of mass, this thing here, we're going to call it d2 dt squared. We're going to call it x, capital X. So this is the position of the whole system. We can think of this as being the position of the entire system. And that's called the center of mass. Now we can do exactly the same thing. We've got a second derivative of the center of mass. That is simply the center of mass double dotted, or that's just the acceleration of the center of mass. So that is an acceleration, and what we see is we can rewrite that the very end of this whole thing is we can rewrite F is equal to m times a.